Okay, my name is Wesley Mdise. So today I will be introducing advancements to one of my friends in the house. So he's a theology student. His name is Nemo. He's doing his master's in theology. So this idea came from a scenario that happened when I was in my room doing statistics. So I noticed that most of humanity cannot do mathematics at all. So if you can look at my basic concept of statistics. So my friend walked into my room, and then when he got there, he saw the things that I was doing, and then he tried to write something. And then if you can look here, God knows what this is. I'm still traumatized, and then it really hurt my feelings that mathematics is a language that is used to communicate almost everything in the world. So I took it upon myself that I would like to introduce basics of advanced mathematics so my friend can stop doing such things and learn at least how to communicate in front of people. Because if something like this happens and then he says he learned it from me, I will never be able to forgive myself. So with that being said, there are a few concepts that I just want to introduce my friend to, because he has a basic knowledge of mathematics from high school. So now, if I were to remove what's on the board now and start with some basic mathematics, starting with numbers. So if we were to start talking about the numbers, so we're gonna start with counting numbers. So you know that when you count, you have numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up and right?
Yes.
So those are natural numbers.
Oh, natural numbers, okay.
Yes, those are counting numbers.
Alright.
Right? So, and then again, we have two other concepts that I want to introduce them to you. The concept of integers, right? So integers are negative and positive counting numbers. So for instance, if you have a 1, then a -1 also forms a part of integer. So counting numbers, we call them 1, 2, 4, etc. Right?
Yes.
These are counting numbers. But when we talk about integers now, we start to talk about the likes of -1, -2, -3, and -4. You see? Up until. You see? But then, you have to know that this number, -1, is not equals to this one. Right? Why? Because this is negative. Eh? And then this one here is positive. So when you add the two numbers, you get a 0. These two. But then again, you have to know that -1, we say -1 is what? Is less than 0. Because if you would remember from primary school, you used to do a number line, right? And in this form, we have a 0 here. So this is a 0, and then it goes to 1, 2, 3. But this side, these are your negative numbers. -1, -2, -3, up until. So these are your integers. So this is the concept of integers, right? And then from integers, there are two other numbers that I would like to introduce them to, that revolves also around integers. So from those, we have what we call our even numbers and odd numbers, right? So when we say numbers, we speak about numbers that are divisible by 2, right? So by that it means if you have 2 and then you divide it by 2, you get what? 1, right? So 2 goes into 2 and then it doesn't leave any remainder. So there's no change. You see? So these are even numbers. Do you get that point? Yeah. So again, if we look at 4, 4 when you divide it by 2, it just gives you what? 2. It doesn't give you any change. By any change, I mean if you were to divide 4 by 2, you don't get the likes of this number, a decimal, and other, maybe let's say 2.5, 2 point something, 2 point.
I get it.
There's no change, you see. And then now, if we were, now I'm gonna introduce another way of writing an even number, right? But now I want you to go back to the concept of an integer, right? So now let's say number which we can represent as an alphabet. Let's say maybe we take K for instance, right? We say K is equals to, so we want to write this K in a form of an even number, right? So when I say K is equals to, but remember, now we want to generalize it. We don't want to say K is equals to 2, K is equals to 4, K is equals to 5. You see, such things. We don't want to say that, but we want this K to represent all the even numbers. How can we write this K in a form that is going to represent all the even numbers, right? So we can say 2 here, right? Because what do we know about even numbers? They are all perfectly divisible by 2, right? So now we introduce an integer, but also this integer, we don't want to introduce it as 1, 2, or 3, or 4. We want to generalize it, right? We can say maybe M, right? And then this M represents an integer, right?
Yeah.
But now this K here, this K represents an even number. Does that make sense?
Yeah.
Because now if M is an integer and then multiplied by 2, it means all the other values that K can be are going to be nothing but even numbers.
Even number. So
Because what? They are multiplied by 2. Remember that if it's multiplied by 2, if it's a multiple of 2, then it means it can be divided by 2.
yeah.
You understand?
Yeah.
So then we say that K is what? Is 2M. Then this is your even number. Then it means all the values that K can be, that are going to be even numbers, all of them. You see? So if I were to introduce a concept that we're going to talk about in a few minutes, is we can say that M is an element of an integer. So now I don't want you to be confused with this concept. Why? Because now we're going to be talking about sets which are going to make it easier for you to understand that concept. You see? But just to give you a brief, we mean that all the values that M can be form part of what? Of integers, right? So when you see this Z is a what? It's a symbol, it's a mathematical symbol that we use for.
Okay. I was about to ask that.
Well, what is Z?
What is that?
Okay. Thank you. Yes, so that is what we use for integers.
Yeah.
You see, because mathematics is supposed to make life easy. We cannot write mathematics like we're writing English. We cannot write paragraphs. We don't have time for that. We're mathematicians. You see. Okay. And then now, this is the concept of what? Of even numbers. Does it make sense?
Yeah.
Okay. Now when we were to skip to odd numbers are the opposite of what? Of even numbers. Right? What do we know about even numbers? Even numbers can be divided by 2 perfectly, and then they don't leave any change. And then when we speak about odd numbers cannot be divided by 2 and leave no change. It's, for example, and then you divide it by 2, then this is going to give you what? 1.5. You see? So it gives you this change. You see? So the same way that we wrote this even number K, we can also write an odd number in a general form. So let's say, for instance, we want to take our odd number to be letter L, right? And then we know that number is not perfectly divisible by what? By 2. So it means in a general form, you can write m. Remember something, eh? M is what? Is an integer. Right?
Yeah.
Integer, don't forget them. -1, negative ones and ones, negative numbers and positive numbers. Those are the integers, including 0. Right? Okay. So now, this form, L is represent what? An even number. Ne? But now, if you want to get rid of that, you can simply just add 1 here. So, this form here is a form of a what? Of an odd number. You see? For example, now, let's take an example. We say 3 is a what? Is an odd number. Right? 3 odd. So, I want to write 3 in this form so that it can be clear. Let's say now, we can say 3 is equals to, we're going to say 2 into multiplied by 1 plus what? Plus 1. You see? Now, our integer here for this m is what? Is 1. But the whole of this thing, 2 multiplied by 1 is what? Is 2. 2 plus 1 is what? Is 3. So that's why our odd numbers are taking this form. Okay. So that is the concept of even and odd numbers. Sense?
Yes.
Okay. Do you have any questions?
Yes.
Is that?
Okay, no, my question, you spoke about an element there. You said M-E-Z.
Oh.
Yes. I want to understand what that element is or what it represents.
Okay. So, okay. So I'm gonna explain an element properly when we speak about sets. But for when we speak about an element, it talks about object. It's an object of a set. You see, so mathematically we say it's an object of a set. But after this here, I just wanna give you another one last concept of these numbers. And then after we talk about sets, and then from sets, I'm gonna be explaining what elements are and how they work.
Okay.
Yes. So now I want to tell you about something called rational numbers. So when we speak of rational numbers, rational numbers. So we speak about a number that can be written in the form of a ratio. So in high school, you remember when you dealt with ratio, you dealt with 2 is to 3, something like this, right? But also, this is also a fraction, right? So our fraction can be written in this form. We can have A over B, right? And then when we speak about rational numbers, if let's say maybe we wrote it like this, A over B, it means your A is an element of Z, so that element is coming back again. You see? A is an element of what?
Z.
Of Z. What is Z again? Do you still remember?
Yeah. Z is an integer.
Yes, Z is an integer. Right? So when we speak about rational numbers, it's a ratio of integers. Right? This one also here, B, is also an element of Z. It's an element of an integer. See? So when we speak about rational numbers are written in this form, A over B. Where is an element of an integer, and then B is an element of an integer. So this is a number system. This is a number system called rational numbers, right? And then when they say irrational numbers, right? Irrational numbers is just the opposite of this. If it cannot be written like this, then it's an irrational number. For instance, if let's say we talk about things like square root of 2, right? Square root of 2 cannot be written in a form of a fraction like that. Well, it can be written in a form of a fraction, but your fraction is going to be like this, root 2 over 1. But now this here is not an integer. You see? But this is what is an integer. 1 is an integer. Remember that any number at 1 is that number. Right? So this here is what we irrational number. You see? Now the difference is that rational numbers can be written in a form of a fraction. Irrational numbers can also be written in a form of a fraction. But this fraction is not going to be an integer over an integer. Does that make sense?
Yeah.
You see? Because if I say it cannot be written in a form of a ratio, then I'll be like, this is also a ratio. But this ratio is what? Is not made up of an integer and an integer. So that number is what? Is irrational.
Okay.
You see?
Yeah.
So to be safe, you can just say an irrational number is any number that cannot be written in this form. And then what is our form? Our form is a over b, where our a is an element of an integer and then our b is also an element of an integer.
Okay.
Does that make sense?
Yeah.
Okay. So this is about our concept of speaking about numbers. Right? And then a sign, a mathematical symbol that is used for rational numbers is Q.
Okay.
Yes. And then now I'm definitely sure now you want to know the symbol that you use for irrational numbers.
Yeah.
For irrational numbers, it's either you use this Q or to give it a cap there.
Oh. Okay.
Then this is your irrational number.
Oh.
Does that make sense?
Yeah.
Okay. So now we wrap up this concept of number systems. So now let's talk about sets, which is the more interesting thing that I wanted you to know. So now we speak about sets. Now in sets, that's where I'm going to explain what that element is and all the other things that come that talks that make up sets. You see, sets. Okay. So I've written my notes here just so that I can get some of the theory part, but I'll be explaining them. So here I've written that sets is a concept from which every mathematical structure is constructed from, right? So this statement, I wrote this statement just to emphasize on the importance of sets, right? We cannot do mathematics without these sets.
Okay.
You see, so we need them mathematically to communicate in maths, because remember, maths is not English. Maths is supposed to be easy on how we write things, how we communicate. You see, so what is a set? So now with definition, we say a set is a collection of objects, right? What are these objects? These objects are elements, right?
Yeah.
So now you've been doing sets all your life, but maybe you just didn't notice that it was sets. For instance, if I were to give you an example of, let's say, alphabets, right? We have alphabets from A up until Z, right?
Yeah.
So those letters A to Z, we can say is a what? Is a set of alphabets. Does that make sense?
Yes.
When you go to the faculty of theology, right? In theology, I understand that there are different streams, right?
Yes.
We have systematic theology, practical theology.
Yes.
What's the other one?
Old Testament.
Old Testament.
Historical and constructive.
You see, historical, constructive. You see, all those things that you just mentioned now, they make up a set of what theology is.
Oh, okay. I understand.
Do you understand?
Yeah.
So mathematically, it's just that we go into the concept of it. It helps us. You see, it helps us to group things. You see, can you imagine now every time when we're there, when we want to speak about the faculty of theology, now we have to write theology is this and theology is that, theology is that. We can just group all of those together and put it in one place and say, okay, if we're talking of the faculty of theology, this is a set of what makes up the faculty of theology.
Oh.
So it is defined mathematically. Does that make sense?
Yeah.
Okay. So that is what a set is.
Okay.
You see, you've been doing sets all your life. And there are many other examples. I'm sure you can think of any example. Would you think of any example that makes up a set?
Yeah. As you explained, alphabets, numbers, colors.
Exactly.
Yes.
Yes. You see? So that is what makes up a set. Like, it's as simple as that, right? So, but it's just that mathematically, then there are ways in which we write our sets. Ne? So our sets are always represented with a capital, with upper letters, right? For instance, if I want to say, if let's say maybe I say faculty of theology, ne?
Yes.
And then I this F then represents the now. I'm not an English teacher. Okay.
Yes.
Okay. Faculty of theology, right? Faculty of theology. Right? So we say F is for our faculty of theology. So if we were to write this faculty of theology in terms of a set, all we have to do then is F. We can say F is equals to, then you see, I used a capital. You don't use a small letters to write a set. Yeah? So now we can say in the faculty of theology, see what I did here. Then I open the curly brace. You see? So now I'm teaching you how to write the sets. Yeah? We can say in here we have what we call systematic theology. Right? We have practical. Right? Yeah. So it's systematic, it's practical. But now, you see, I've separated the two with a what? With a comma here. Right? So when you are done mentioning all the things that makes up the faculty of theology, what you do is what? You come here and you close this.
Okay.
You see?
Yeah.
So now you've written a set. You see? So now you asked a question about elements earlier on, right? So when we talk about the faculty of theology, now you have systematic theology, practical theology, right? The element of a set.
Okay.
You see?
Oh, yeah.
Yes. These are what you call the element of a set. You see? Yeah. So this is what we meant by a collection of objects. These objects are what? Are elements. Does that make sense?
Yeah, it makes sense.
Okay. So now you've learned how to write a set. This is how. You see, this is the form of a set. Yeah? So now I want to show you another thing. Let's say now we say systematic theology is what? Is X. Yeah? And then now we say practical theology is what? Is Y. Then so now let's write this set of ours in terms of X and Y. So we can just say F is equals to, then curly braces. Then since our systematic theology is what? Is X, we put an X here. And then since our practical theology is what? Since our practical theology is Y. Then we put a Y here. You see? So this is our set. You see? So now I want to show you a certain way in which I wrote a set earlier on when we were speaking about numbers. Right? So now I want to tell you that this X belongs to this set F. Right? So how am I going to write that? I'm going to tell you that X. Anna, what did you say this X and Y are?
Systematic.
No, in terms of we said these are objects.
Objects.
Or what?
Elements.
Or elements,
Yes.
right? So these are objects of, yeah?
Yes.
So now, I want to tell you that this X belongs to this set, right? So how will I do that? I'm going to say that this X is an element, right? So simply I'm going to say element with this symbol here.
Oh.
You see? An element of what set? Of set F. So then you come here. So this thing and this thing are the same thing.
Yeah.
So in the on, that's why I said, I remember you said I said X is an element of Z. Right? So if I were to write this in this form, yeah, I can just say Z is equals to, remember, when you speak about a set, you have curly braces. Opening your curly braces, closing your curly braces, and then what is your element? X. You see?
Yeah.
This is a what? This is a set. Does that make sense?
Yeah, it makes sense.
See? So this is how we write set. Yeah. So now, if we get to a point where we have, let's say maybe we want to write numbers from 1 up until 10, right, in one set. So what we can do is that we don't have to write all those numbers saying, okay, let's say maybe our set is equals to our set is Z. We don't have to say Z is equals to, and then open curly braces, write 1 up until 3, 4, 5, 6. You see, so it's training, but there's also a way in which you can write that. You see, so the trick is to see if something follows a certain pattern. You see, once you spot that pattern out, you can use 3 dots inside your set. So by these 3 dots is what you're saying. You're saying that, let's say for instance, now we want to take a set of, let's say Z is equals to, let me write numbers 1, 2, 3, 4, 5, 6, 7, and 8. Okay, let's stop at 8. Yeah. So I want to write this set, but I can see that this thing follows a particular pattern. So my set increases by what? By 1. 1, 1, 1, 1. So that's a pattern. You see. So what I can do is I can just say, okay, my Z has to be 1, 2. You see? Or maybe let's say maybe we can just say 1, 2, 3. Just to demonstrate the pattern. Let's see. 1, 2, 3. And then you put a comma, 3 dots, 1, 2, 3. What is the last number in my set? Is this 8, right? And I can put another comma and say 8, right? And then close my set.
I have a question.
Okay.
So when you are doing like the representation you did then, so you must always write maybe the first number, second number, and then let's say George, and then the last number which the set closes with.
Yes.
Alright.
Because you see now you are not limited to a specific set of numbers. So you just have to demonstrate the pattern. Remember that we are communicating mathematically. You see. So if you do something like this, and then okay, you give to someone who was not with you when they write, and then you tell, okay, no, this thing is like this. You see. So they have to tell you, okay, oh, this is 1, 2, 3, and then the numbers. So they've already seen the pattern here. You see, and then you give them the last number. For instance, if I can do this, say Z is equals, and then I say 1, and say 8. You can see a pattern here. The number that follows can be 2, it can be 3. We just don't know. You see. So now I have to come back to you and say, no, you see, you gave me 1 to 8. What did you mean by this? You see, I have to come back to you. But when it's like this, I'm like, okay, it's 1, 2, 3. Oh, okay. Up until 8. Okay, I've seen a pattern here. Does that make sense?
Yeah, it makes sense.
Yes. So we're communicating. Speaking, we're communicating mathematically. Yes. Okay, so Does this concept make sense? Okay, so now I want to give you another concept. You see, when we're speaking of a set, let's say maybe, let me give you a set of, let's say Z is equals to 2, 4, 6, 8. You see? So with this pattern, can you see what's happening inside this set?
Yeah.
It's 2, 4, 6, 8. Which numbers do you see in here?
Even numbers.
Exactly. So this is a set made of even numbers, but it starts at 2 and ends at 8. You see? I'm glad you managed to see that.
Yeah.
You see? So this set has how many elements?
1, 2, 3, 4.
It has 4 elements. You see? So if you want to spot the number of elements that are in a set, you check, okay, 8 plus 1, 2, 3. You see? So you just count to say, okay, after every comma, how many numbers do I have? You see?
Yeah.
Or how many objects or how many elements, then you can tell the number of elements. You see? So now we're gonna say this set, mathematically speaking, it has the cardinality of 4. Cardinality. You see? So cardinality is just the number of elements in a set.
Okay.
You see?
Yeah.
So when it's like this, you say, okay, no, okay, I can see this set. So maybe you're talking to someone. You see? If you're speaking to a mathematician, you say, no man, I was working with this set. It was a very small set, just the cardinality of 4. You see, already that person knows, oh, okay. So this person was working with a set that has 4 elements inside it.
Okay.
You see, so that's the word that we use. This set has a cardinality of 4. Then it means it has 4 elements.
Yeah. Okay.
Does that make sense?
Yeah, it makes sense.
Okay. So this here is just a basic understanding, a basic theory of what sets are and how they work. I hope you managed to get something out of this.
Yes, I understand sets now.
Okay.
Yes.
So is there still any questions that you have?
Yeah. I have a question.
Yeah.
Okay, so my question is this. Can you then have a set that has no elements?
Good question. Yes, you have a set that has no elements. And that set, when you're writing it, you want to write it like this.
Or with nothing?
With nothing. This is an empty set. But there is a mathematical way of writing this. You see, we can use what? A symbol like this. And then we say this is equals to, this is an empty set. So we call this an empty set. And then you can be asking, when will you use an empty set? If I were to give you a practical example, let's say maybe you want to do a list of items, right? So when you want to do a list of items, you don't know how many items you want to put in that list as of yet, right? But that doesn't mean you're not supposed to create a list. You can create a list, put it there, just to remind yourself that, okay, I have a responsibility to do of adding certain items to the list. You see? Yeah. It's like maybe, for instance, maybe when you want to do your groceries, right? Maybe you don't know, it's probably maybe around the 15th, you don't know how many items you're going to need, you see? So for you to remember that, okay, I have a responsibility of creating a list, you can just write your grocery list there, grocery list, okay. When something finishes in your cupboard, and then you go there, okay, this and this and this and this finished, and then you go and add it to what? To that empty list.
Yeah.
Does it make sense?
Yeah.
So it is useful to have an empty list in mathematics. It's also the same thing. We might be in a position where maybe we want to do some mathematical calculations, right? Yeah. We don't know the answers to those calculations as of yet. Maybe it's using a program. Program will be running. So we can use an empty list to do what? As the program runs, it can take the answers that it gets and then put them inside that empty list. And then we can finally get what we're looking for. You see? So that's when you use empty list. Yes. So now I want to show you something. And just to wrap up this with our last concept. Of this session, I want to give you something like this. Let's say this is B. Right?
Yeah.
If this circle represents B, and then I can have another small circle in here, it's A. Right? So, you see that this A is inside this B. Right?
Yeah.
So now, let's say that B is a set, represent a set, and A represent a set. Right? So what does this tell us about set A? It tells us that set A is inside set B. Do you get that?
Yeah.
So what do you say? Mathematically speaking, we're gonna say A is a what? Is a subset of B. You see? A is a set on itself. Ne? But it's a set that is inside B. So A is a subset of what? B. Of B. Does that make sense?
Yeah, it makes sense.
So it's the concept of what? Of subsets. Right?
Yeah.
So we're gonna say A. Ne? If maybe let's say I can write it using numbers. Ne? Let's say maybe we say our B is equals to 1, 2, 3, 4, and 5. Ne? A has to contain all the elements that are in B for it to be a subset of B. Not all of them, some of the elements that are in here. Right? For instance, our A can be 2 and 3. Right?
Yeah.
Then our A is a what? Is a subset of B. Why? Because when you look at this set B, it has 2, it has 3. That's the elements. You see? So mathematically, this is how you represent your what? Your subset. So we're gonna say A, I hope I got this right. Something like this. You see? Then A, this means that A is your what? Is a subset of B. Does that make sense?
Yeah.
Yes. So this just wraps up the basic knowledge of sets. Ne? So meaning that when you speak about sets, it's just about everything that I have explained, and then also the number systems. So it gives you a basic knowledge of how to communicate mathematically using those numbers and how you can group them. So these concepts are the concepts that you can apply in your day-to-day basis on maybe how you do your lists, how you group your things. You see, so you can use these mathematical concepts to represent this. Yeah.
Yeah.
Okay. So, do you have any questions?
Yes, I have a question.
Okay.
So the question is that how many subsets can you have in one set, and how would you represent it?
Okay. So you can have as many subsets at one set. So it's just going to be controlled by your you see. So this set, we call it the universal set. You see, it's all the set that contains a subset. So now, if I were to show you how to write a subset, let's say maybe let's take one set. Say Z is equals to say 1, 2, 3. Yeah, this is fine. Yeah? Okay, so now I want to show you a very important concept when it comes to writing the subsets, right? So we can say 1 alone, right, is going to be a subset of this set. This element alone makes a subset of this, right?
Yeah.
And then we can also say 1 and 2 makes a subset of this. We can also say 1, 2, 3 makes a subset of this. You see, this has all the elements that Z has. This has 1. This one, Z has 1. 1, 2, Z has 1, 2. You see? Also, you can use this one, 2. You see? So, 2 is also a subset of this set. 3 is also a subset of that set. You see?
Yeah.
So now, these are not all the subsets. There's one subset that is always there in every set. Yeah? It's an empty set. Do you remember we spoke about an empty set?
Yeah.
So an empty set also forms a what? A subset of this. So to answer your questions, how many subsets can we have? Then we're going to be controlled by how many elements are in our set. Does that make sense?
Yeah.
Set. And then this is also one last concept. When they tell you that they want the power of a set, so they want you, when we speak about the power of a set, we're speaking about how many subsets are there in one set. Does that make sense?
Yeah.
The power of a set is what? How many subsets are in that particular set. That does it?
Yeah.
Okay.
Makes sense.
So this here, it wraps up the knowledge that I wanted to pass to you of how to communicate with mathematics effectively. So do you at least do you have an idea of?
Yeah, now I have an idea
Of what was happening?
Yeah.
Okay. I'm glad.
Thank you so much for the lesson.
All right. No, you're welcome. The other thing that you wrote on my whiteboard traumatized me. I had to.
Now at least I have a basic understanding of communicating numbers. Yeah.
All right.
Yeah.
No. I'm glad I could be of assistance.
All right.
All right. Thank you very much.
Thank you.